One of the basic rules of the universe is that nothing is perfect. Perfection simply doesn't exist without imperfection. Neither you nor I would exist. Stephen Hawking, a scientific genius, revolutionized our understanding of the universe through his profound contributions to cosmology. Despite battling owls, his work and enduring legacy continue to inspire and shape scientific exploration. Hawking's groundbreaking discoveries, particularly his work on black holes, pushed the boundaries of knowledge and challenged established theories. Stephen Hawking's black hole theory has been debated by scientists for years, but we may finally have proof that it exists thanks to the James Webb Space Telescope, JWST. Known as one of humanity's most advanced astronomical tools, the Webb Telescope, through its unparalleled capabilities, has enabled the discovery of a wide variety of black holes, ranging from faint distant ones to a few that are exceptionally bright and lie even farther away. This data is about to alter our perception and understanding of these enigmatic celestial bodies. Join us as we dig deep into how James Webb could change everything we know about black holes. Black holes can often be misunderstood or mistaken for something evil. What are they, actually? Well, they're interestingly fascinating objects in space, places where matter has been crunched down into an intensely compact area. If Earth were hypothetically crushed into a black hole, it would be under an inch across, yet the object would still be extremely massive, as it would contain the entirety of our planet's mass. The result? A place with a gravitational pull so strong not even light can escape. This can make black holes seem like omnipotent, terrifying objects with an insatiable diet for stars and planets. In the mind of the public, black holes are often imagined as huge cosmic vacuum cleaners that suck up everything in their path. This is an evocative but incorrect idea. A black hole is not and does not create a vacuum. Quite the opposite, it attracts through the effect of gravity. Because the density of its mass is so enormous, it follows that we should have nothing to fear if the sun were to be replaced by a black hole of the same mass. Though our world would be much colder and darker, the planets would continue to orbit undisturbed because the mass of the black hole would be equivalent to that of the sun. The existence of black holes stems from the theory of general relativity published by Albert Einstein in 1915 and the subsequent work of Robert Oppenheimer, Carl Schwarzschild, Subrahmanyan Chandrasekhar, and others. Space and time form a fabric that is curved by mass like a trampoline. A black hole is a ball so heavy that it has at its center a singularity, a region so infinitely dense that it collapses the bottomless trampoline. Any object we place nearby will tend to fall towards the ball, so the gravitational effect of the black hole is felt in its surroundings. Astrophysicists have been able to identify many such black holes by discovering cosmic objects orbiting around an apparent nothingness. This gravitational pull reveals the presence of something that is otherwise completely invisible. These black holes are often called stellar black holes. They originate after the death of a star whose internal gas pressure pushing outwards can no longer counteract the enormous force of gravity, which compresses its remaining matter until it collapses into a black hole, a couple of dozen times the mass of the sun. These are tiny compared to those that can store up to millions of solar masses, the supermassive ones that sit at the center of many galaxies. At the other extreme, there are black holes even tinier than the stellar ones, micro-black holes formed in the early universe. Regardless of their size, they are all surrounded by an invisible boundary called the event horizon, the point of no return beyond which nothing can escape, not even light. Around that horizon, the masses of dust and gas are so accelerated by the gigantic influx of gravity that they heat up and glow, emitting radiation and sometimes forming an accretion disk, which allows us to observe the shadow that the black hole itself casts on the luminous ring. Thanks to this effect, the Event Horizon Telescope, an international collaboration of ground-based radio telescopes, succeeded on April 10, 2019, in providing humanity with the first image of a black hole, which occupies the center of galaxy M87. In 1974, a study by Hawking published in Nature shook the science of the time by proposing that black holes were not so black, nor did they grow endlessly as physicists, including himself, had previously assumed. His genius was to combine two traditionally irreconcilable worlds: general relativity, the Einsteinian gravity used to explain the formation and evolution of black holes, and quantum mechanics, which describes the nature of the subatomic world. In his earlier papers, Stephen Hawking had shown how relativity led to the singularity of a black hole, but then it was necessary to crack open the quantum chest to explain what was going on there. As physicist Ethan Siegel explained, quantum theory suggests the continuous creation of virtual particle-antiparticle pairs that annihilate each other almost instantly. But if this happens right at the edge of a black hole's event horizon, it may result in the negatively energetic antiparticle falling inwards, stealing energy from the black hole and its partner escaping into space with identical positive energy. Eventually, this would lead to the total evaporation of the black hole, with no matter or energy escaping from it. Although, as Hawking pointed out in the study, for a black hole of solar mass, this is much longer than the age of the universe. In much smaller black holes, it would be faster, culminating in a final explosion equivalent to 1,000,000 1-megaton hydrogen bombs. Hawking's demonstration that black holes can emit radiation is his most important result, says Juan Meldicena, a physicist at Princeton's Institute for Advanced Study. But at the time, this Hawking radiation opened a real schism between relativistic and quantum physicists, as the latter now had a radical problem. If, according to quantum physics, the information associated with particles is never destroyed, but no matter or energy ever escapes a black hole, how can a black hole simply disappear, taking this information out of existence? Hawking radiation is widely accepted in current physics, although it is almost impossible to measure and therefore verify. Paradoxically, it is expelled in greater quantities by smaller, undetectable black holes, while the larger ones, those that astrophysicists can study directly, produce so little that it is indistinguishable from the cosmic background radiation. But at least a similar phenomenon has been recreated in the laboratory. Researchers at the Israel Technion Institute of Technology have generated analogs of tiny black holes that work with sound rather than light and have managed to demonstrate something similar to Hawking radiation. These experiments have confirmed two of the physicists' predictions: that the radiation is spontaneous, generated from empty space, and that it is stationary, it does not change in intensity over time. But for its part, the so-called information paradox has remained the most important of the questions raised by Hawking's work. And the opinion of Meldicena, the question has kept physicists busy for the last half-century, including Hawking himself, who until his death searched tirelessly for a theory capable of unifying general relativity and quantum mechanics. In other words, a quantum theory of gravity that describes what happens inside black holes. The famous physicist's last words proposed a solution to information retrieval. In the 1970s, John Wheeler, who popularized the term black hole, and Jacob Bekenstein claimed that black holes have no hair, in the sense that the only properties a black hole could have were its mass, its electric charge, and its angular momentum. Thus, if one observed a black hole, you could tell nothing about how it was formed, since all other information is lost inside it. The event horizon is, so to speak, a denuded boundary shorn of all information. However, in 2018, Hawking, Perry, and their collaborators found a theoretical way to propose that black holes can have soft hair. If you will, an infinite collection of extra properties that a black hole can have, says Perry. As Amica Taylor, a physicist at the University of Southampton, whose PhD thesis was supervised by Hawking, says, this metaphorical hair suggests ways in which black holes may keep track of information at their surfaces so that this information is ultimately recovered. But Perry cautions that while these ideas advance a possible resolution of the information paradox, they are not the final word. Recently, other models, in addition to soft hair, have emerged. There have been exciting developments about recovering information from black holes over the last year or two. According to Tom Banks, a Rutgers University physicist who shared scientific discussions with Hawking, Britain's contributions have been the most important single piece of work contributing to our understanding, still very limited, of the connection between quantum mechanics and general relativity. This is a road that has been traveled for half a century, and where much remains to be done. Progress is good, but the timescale for solving these deepest of all problems is long. Andrew Strominger, co-author of the soft hair study at Harvard University, says, "We have been trying to understand black holes for 100 years. I hope we can wrap it up in another 50, he says, responding to the expectations of the scientific community. A recent revelation from the James Webb Space Telescope, one of humanity's most advanced astronomical tools, has left scientists astounded, shedding light on the mysterious nature of black holes. Previously, the existence of black holes in the cosmos had always been an area of extensive study. Yet JWST revelations have exceeded astronomers' wildest dreams. The JWST, through its unparalleled capabilities, has enabled the discovery of a wide variety of black holes, ranging from faint distant ones to a few that are exceptionally bright and lie even farther away. This data is about to alter our perception and understanding of these enigmatic celestial bodies. Many of the newly discovered black holes lie at redshifts between 4 and 6, corresponding to a universe aged around 1 to 1.5 billion years. The JWST's discoveries at these intermediate redshifts are about twofold more than the astronomers' initial estimates, prompting further study and introspection into these results. The JWST's detailed observations have also unveiled some of the most remote black holes ever identified. One confirmed discovery lies at the heart of a well-studied galaxy, GN-Z11, exhibiting a redshift of 10.6. This suggests that the seeds for black holes had already manifested and started to form supermassive entities astonishingly early, about 400 million years post the Big Bang. In fact, the existence of cosmic titans, which have masses millions and even billions of times that of the Sun, doesn't constitute a problem when supermassive black holes are seen in the local universe. However, supermassive black holes become an issue when they are seen in the early universe and they already have masses equivalent to billions of suns. That is because there must be some mechanism that allows supermassive black holes to rapidly gather mass and grow to such giant sizes. Yet, all the existing mechanisms for this growth suggest this process proceeds too slowly for objects like this to exist just after the Big Bang started. Royal Society Universe Research Fellow at Mayu University, John Ran, describes the problem with a somewhat disturbing analogy. It's like seeing a family walking down the street and they had 2 6-foot teenagers, but they also have with them a 6-foot-tall toddler. That's a bit of a problem. How did the toddler get so tall? He says, and it's the same for supermassive black holes in the universe. How did they get so massive so quickly? This issue is further complicated when the James Webb Space Telescope discovered the most distant and earliest supermassive black hole located at the heart of the galaxy SPT 0311-58. This black hole has a mass of 9 million times that of the Sun, which makes it relatively diminutive for a supermassive black hole. Yet, even at this size, the existence of this just 570 million years after the Big Bang is challenging to theories of black hole growth. And this 9 million solar mass black hole wasn't alone. The same observing campaign that revealed this supermassive black hole, the Cosmic Evolution Early Release Science (SEWERS) survey, also uncovered 2 other supermassive black holes that existed both 1 billion and 1.1 billion years after the Big Bang. According to Canadian University of Western Ontario professor Shantanu Basu, with each new discovery, the constraints on our existing ideas become stronger. We were worried when supermassive black holes were seen 800 million years after the Big Bang. SEWERS just increases the challenge tremendously, Basu says. This suggests that supermassive black holes are common in the relative infancy of the universe, not some cosmic rarity, thus putting more pressure on the search for a mechanism to explain how they got there. Discounting primordial black holes, hypothesized to be left over after the Big Bang, the 3 main categories of black holes are stellar mass black holes, intermediate mass black holes, and supermassive black holes. Stellar mass black holes form when the most massive stars run out of fuel for nuclear fusion and can no longer support themselves against their own gravity. As the outer layers of these stars are blown away in huge supernova explosions, the cores collapse to create stellar mass black holes, regions of space with a point of infinite density called a singularity at its center and an outer boundary called the event horizon, where the force of gravity is so great not even light can escape it. Supermassive black holes must form in a different way from stellar mass black holes, as it is impossible for a star to be large enough to have the initial starting mass to shed mass as it evolves through events like the supernova that accompanies the gravitational collapse of the star, but still leave behind a core massive enough to become a supermassive black hole. For many years, astronomers have believed that supermassive black holes could start their lives as seed black holes that are much smaller, growing by first feeding on material and then merging with other black holes when the galaxies they reside in collide, something that also provides these budding supermassive black holes with gas and dust to feed on. The growth of stellar mass black hole seeds could happen when these cosmic seeds find themselves surrounded by vast amounts of matter and greedily feast on this material to rapidly grow into supermassive black holes. This process should be stunted, however, by something called the Eddington limit. The luminosity and brightness of a feeding black hole are proportional to the rate at which they are gathering mass. The faster a black hole consumes matter, the faster it grows, and the faster it grows, the more electromagnetic radiation is blasted out by its surroundings. But if the electromagnetic radiation emitted from around a black hole, in the form of jets, is intense enough, it physically pushes material away. This means the faster a black hole eats, the more likely it is to have its food supply interrupted and pushed away, thus halting that growth. The Eddington limit means that it should take black holes billions of years to accrete enough matter to reach supermassive black hole status. RAN is part of a team of researchers that investigated something called super Eddington accretion, which could account for the rapid growth of supermassive black holes in the early universe. This wouldn't, he explained, be anything particularly special, just a more rapid version of normal black hole feeding. This would lead to rapid episodes of feeding, with material pushed away by jets halting feeding and thus cutting off the jets. This then allows the material to fall back to the black hole, thus triggering another bout of frenzied feasting. Reagan and colleagues found this explanation unsatisfactory, however. He said, if you average this feeding cycle over time, it is actually less than the Eddington rate. It might be okay for 1 or 2 cycles, but overall, over time, it's not great because it just can't and it doesn't go continuously, so we didn't find that this was a great mechanism to really explain supermassive black hole growth, he said. According to Reagan, another possibility that could explain the rapid growth of supermassive black holes is the idea that the seed black hole from which they grow is massive in size. Massive black hole seeds would still have to get into these dense environments, but at least they would have a head start on smaller seeds. Going back to the 6-foot infant analogy, Reagan explains that the growth of this child is even tougher to explain if it was born with a length of an average infant. But if this child was born and it was already 3 feet long, its transformation to a 6-foot-tall toddler isn't quite so tough to explain. After all, the problem with investigating this is, unlike toddlers, black holes lack any characteristics beyond their mass, angular momentum, or spin, and their electric charge. Scientists call this the no-hair theorem, and it means that black holes are deceptively simple and don't carry information about their histories or evolution. Basu added that observing the feeding process that is bulking up black holes in the early universe hasn't been possible as it has been happening so far away from us. But detecting supermassive black hole feeding may be possible in the future. The hypothetical supermassive stars in the early universe would be extremely luminous, perhaps 10 billion times as bright as our Sun. It's possible that the JWST or other upcoming space telescopes could detect such objects if they are present as late as a few 100 million years after the Big Bang, Basu reported. Despite these issues, Reagan is confident that by investigating black holes in the early universe and by potentially discovering heavy seeds, scientists will soon be able to build a supermassive black hole growth picture. In particular, he pointed to the launch of the Laser Interferometer Space Antenna, LISA, a space-based gravitational wave detector that will help scientists better constrain the demographics of black holes in the early universe. We made a huge amount of progress in the last 10 years, and we will continue to make massive progress over the next decade as well. Extrapolating out from these demographics will give us a very, very good handle on the number of mergers happening in the distant universe involving black holes in exactly the mass range we need, with masses around 100,000 times that of the Sun. I think it is very probable we will have solved this problem in the next 5 to 10 years, he said.